Okay, hello once again. In our first video that I shared, I talked about how you can locate the root of a given function using graphical approach. We went ahead and looked at the two approaches you can use under graphical approach. We said you can use single graph approach or two graphs approach. For single graph approach, we said you plot the function the way it has been presented to you along the domain given. For instance, sorry, the line is not straight. Like this. You plot it, and after plotting it, you observe whether it crosses the x-axis or not. Let's see. Let me get a line. I think this is going to work. You have a line like that, and you have another one. Let's say you have another line. It's like this. These are axes, not just lines. We have this and that. So let's say this is our x-axis, and this is our y-axis. This is x-axis, and this is y-axis. We said if you draw a graph and crosses the x-axis, let's say like that. Let's say this is point A, this is point B, and this is point C, this is point D. We will conclude that this function you plotted, the function you plotted has two real roots, one between A and B and another one between C and D. We also talked about the definition of a root. We said a root is simply a value of x that we substitute in this function, and the function becomes 0, something like that. So you notice that at this point here, the function is 0, and at that point there, the function is 0. So you conclude that the function has two real roots. The number of times the function crosses the line crosses the x-axis will show you the number of roots that the function has. In this case, it has two real roots. Then, of course, if you plot and the function and it looks like this, if you plot and you end up with a graph like this one here, if you plot and end up with something like this, then that would mean that plot and come up with something like this. Notice that this is not crossing the x-axis at any point in the interval, let's say AB. This graph is not crossing the x-axis at any point. So here I would say that the function you plotted, f of x, has no real root. This one has no real root in the interval AB. It does not have real roots. If it doesn't have real roots, what does it have? Then it has unreal roots, which roots we refer to in mathematics as imaginary roots. It doesn't have real roots. We look at that more when it comes to complex numbers. That is for single graph plot. Then for a two graphs plot, we said you plot the two functions, you plot them, and you look at the point of intersection. The point of intersection, you split the function given into two. We said preferably a linear graph and a linear function and non-linear function. Then plot them on the same axis and not the points of intersection. So in this case, these are intersecting twice here and here. It would mean that this function you split has two real roots. Then also you look at the intervals. You produce this one the x-axis, produce this one the x-axis, and note if this is AB, B is here, this is A here, C here, and D here, then this would mean that the roots lie between C and D and A and B respectively. I will not spend a lot of time on that. You can refer to the previous video, and that will take you have a review of what we looked at there. But today I want basically to introduce sign change method, and sign change method doesn't differ a lot from the graphical approach. In fact, this is like the short form, the summary, the quick form of locating the root, but it also it is not very different from sign change method, from graphical method. Let me give you a simple illustration here that we're going to use to develop our concept of sign change approach. Now, if I have, of course, the x-axis as usual, then I have the y-axis also. I have the y-axis, something like that. Yes, something like this. Now, you draw your curve. This is my, this side, let me get the pen. This is my y-axis, of course, which I have as f of x, and this is my x-axis. Now, we're saying if the root exists, then this the curve should cross the x-axis. Let's say it has come like this. It can come like that. Something like this. It has crossed the x-axis in that time, in this interval. This is my function, f of x, that I'm plotting. Now, if I have a at this point, and I have b at this point, let me look at how f of x is changing. It is coming from the negative side of the axis and going to the positive side of the f of x, or the vertical axis. Now, when I substitute, if I substitute a in this function, it gives me a negative value. If I substitute b in this function, it has given me a positive value. There is a change in sign. So before that, of course, using the graphical approach, we conclude that f of x has a root between in the interval ab, because it's crossing the x-axis in that interval. But also notice that when I put a in this function, it gives me a negative value, and when I substitute b, it gives me a positive value. So therefore, my f of x is changing sign. Remember, we have here, this is my f of b, and my f of a will be somewhere here. So f of a and f of b are going to have opposite signs. They are having opposite signs because this one lies below the x-axis, and not the values of f of x. The values of the vertical axis below the x-axis are all negative. Then the values of the x-axis, the values of the vertical axis above the x-axis are all positive. So notice that this one's above and this one's below. So there is change in sign in the interval AB. So therefore, we can also conclude just by mere looking at the signs, we can simply say the root exists. How would the graph look like if the root doesn't exist? We know that already. It doesn't cross the x-axis from our the content we looked at earlier. When I draw something like this, and I have, of course, the x-axis also. I have something like that. I draw my line. It may not cross the x-axis. It may remain on the negative side, or it may be on the positive side. Let me see if it is like something like that. When I put, of course, let me have my a here. Let me have my b here. This is my x-axis. This is the y-axis. Now, when I substitute, of course, y-axis, but it is having f of a, f of x. Now, when I put a in this function, my f of a will be somewhere there. F of a is there. And when I put b, my f of b will be approximately here. Now, you notice that f of a and f of b are having the same sign. They are both lying on the positive side of the y-axis. There is no change in sign. F of a and f of b have the same sign. And therefore, even using graphical approach, we know if the graph is like this, we conclude by saying the function f of x has no root, has no real root in the interval ab, because it's not crossing the x-axis in that interval. So therefore, we say it has no real roots. But you also notice that the signs of f of a and f of b are the same. They are both positive. So that also shows us that if the signs of the function, if the sign of the function doesn't change, if it is the same sign, then the root does not exist in that interval. In that interval there is no root, no real root of the function. If, of course, we're looking for one root, there's no real root of the function in that interval. If they say there's only one root, if you know that there's only one root, of course, if there are many roots, it may not change. Of course, it may go to negative and come back to positive. Just like in this case, why this formula sometimes confuses is when you have more than one root. For instance, when the curve comes here, then it goes like that. It has crossed, but again come back. So you may get f if let's say b is here and a is here. You may get f of a being the same as f of this, having the same sign as f of b. So then you conclude that there is no root. Yet there are two roots in between, one that the curve has changed and come back. So in this case, when you're using this method, we're looking at the case of one root, if there is only one root. Okay. And in questions you're going to meet here, most of them will be saying, show that it has only one root, show that it has only one root. But if there are many roots, then this method may be a bit misleading. You get it? Maybe a bit misleading. So in most of the questions you're going to find, they'll say, show that there is one root, show that there is a real root, show that there is a real root. But if there are more than, if in a given interval there are more than one root, then this method may not be very appropriate. Or if the question says, show that there are roots using sign change, then that means that you have to split the interval, that you identify those different intervals within which the root lies. Okay, so that's what we do. And how do we consider, how do we handle such questions then? Let me create more space here. How do we handle this challenges then? So we shall say, if you've been given f of x, given f of x equals to 0, and the domain, of course the domain, these are the values of x that you're going to use, the input values, the domain AB, that means that the interval AB. If the root lies in AB, then what do? You obtain f of A and f of B by simply substituting, of course, simply substituting the function. After that, the next thing is you observe the signs. Observe the signs of FA and FB. Then the next one, the root exists. The root of f of x exists if there is a change in sign. There is a change in sign. If there's a change in sign. Sorry. Take this if there's change in sign. So let me get this. Documenting. Sorry, let me put something right here. Yeah, so it exists if there is a change in sign. If there is a change, in sign. There is a change in sign, yeah. So that is what we do. So simply get the domain given, substitute the function. If they say the root lies between A and B, get the value of f of A, get the value of f of B, and after doing that, you substitute those values in the function, then observe the signs. If there's change in sign, then the root exists. If doesn't, the root doesn't exist. So what do we do? Sometimes this is what we do. How would we conclude here if the root exists? We have a clear conclusion. If the root exists, how do you conclude? So the conclusion that we use here, we shall say, you also obtain so how do you conclude? The most important thing here is concluding, the conclusion. You say, yeah, you obtain f of a times f of b. Then you say, since f of a times f of b is less than 0, then the root of f of x exists. Exists in the interval AB. That's how we conclude. That's one of the ways. That's if the root exists. If the root exists. Then the other way, that's one of the ways of concluding. The other one, you can say, since there is change in sign, since there is change in sign, then then f of x equals to 0 has a real root, in the interval, AB. Has a real root in the interval, interval AB. So that's how we conclude. And this summarizes the sign change method. So the things are clear. You have a function, they'll give you a function. And what you do, your function has to be in the form f of x equals to 0. So you have to rearrange a few things if it's not rearranged. Then they'll give you the domain. The domain, those are the values of x they want you to investigate and confirm whether the root lies there or not. So I'll simply get my value, for one value, put it there, get another one, substitute there, and I note the signs. If there is change in sign, I conclude that the root exists. We've just seen from the simple illustration I gave on the graphs above that if the root exists, there should be change in sign. If the root doesn't exist, then there's no change in sign. So if I get f of a equals to positive, f of b is also a positive value, then there is no change in sign there and the root does not exist. But if I get f of a as being positive and f of b as being negative, or either way, fb is negative, fa is positive, in that case the root exists because of a change in sign. So that's the basic thing that you need to do. But then the other thing, the most important thing is conclusion. How do you conclude? I can conclude by getting a product of fa times fb. Of course, when I multiply a negative and a positive, it must give me a negative. And all negatives are less than 0. So the conclusion that we agree on here is this one. You simply try to get the product of the two. fa times fb. If you see a negative value, of course, all negative values are less than 0. So you say, since fa times fb is less than 0, then the root of f of x exists, or the real root. In fact, we're looking for the real root, not just a root, because you can have an imaginary root. In future, you look at that. So then the real root of f of x equals to 0 exists in the interval AB. That's one way of concluding. The other one is Since there is a change in sign, then f of x has a real root in the interval ab. That's what you do. Let's have some examples now. Of course, this summarizes sign change method, but let's do these few examples and we'll see. We will try to put what I'm saying in practice. So the first question says, show that the root of the equation x exponent x minus 2x plus 5 equals to 0 lies between 2 and 3. Lies between 2 and 3. So let me get a calculator. Since we're going to be computing a few things. But I can't see the calculator. I think I'll get. We shall need a calculator for that. I can't see it. Okay. If there's no calculator, I shall find other ways of sharing it. I'll use my phone for the calculator. A moment. I'll put the calculator. Okay. Trying to get a calculator here. A moment. Okay, so calculator. Okay, I have it ready. So we have they're saying show that the root of the equation x exponent x minus 2x plus 5 equals to 0 lies between 2 and 3. Remember, this can also be done using graphical method. But sign change method is a summary, is a bit short. So when you find such a question, you may not waste time going to a graphical approach, unless the question has restricted you to using graphical approach. But for now, this is an open question, so we may not waste time looking for the graph paper and going to the graphical approach. So let's see how we can do this. Let's see how we can do this. We're going to use sign change approach. So when you find a question and you have not restricted you to graphical approach, simply use sign change approach and continue, because for it is a bit short. So what we do here, we shall say let f of x be equivalent to x exponent x minus 2x plus 5. That's what we have. Then the other thing we're going to do is to get f of 3. F of 2 will be the same as 2 exponent 2 minus 2 times 2 plus 5. Something like that. This is 2 plus 5. So what does this give us? We're interested in the sign. What does it give us? We shall, let me check here. We are having 2 exponent 2, 2 exponent 2. Trying to be faster. Where's exponent? Oh, this calculator won't do much. This calculator will not do much. Let's just check here. I think the calculator. Okay. Let me see. You have to be patient a bit as I look for the calculator here. We need a calculator. Okay, so let's continue. I use my calculator. Let me get the calculator value. So if we put 2 exponent x, that we shall get 1.1353. 1.1353. Then f of 2 will be the same as, not f of 3 now, we're putting 3. F of 3 will be the same as 3 exponent 3 minus 2 times 3. This is what we're putting, plus 5. This is 3 plus 5, which will give us, that gives us, when you put that, it gives us negative 0.8506. Negative 0.8506. Now, the fact that there's already a change in sign, you know that this one, f of 2 has given us a positive value, f of 3 has given us a negative value. The fact that there's a change in sign, then the root exists. But you don't just leave it here. You must write the conclusion. You must write it here. And I said you conclude, there are 2 ways of concluding. You can say, get f of 2 and get times f of 3. What will give us, what this give us is of course the same as 1.1353 times 0.8506. Of course this is negative. What does it give you? What does this give? This is 6. What does it give? Let me try using a calculator here. It gives us negative 0.9657. Negative 0.9657. So you know that this is negative and it's below 0, of course. So we shall simply say, since f of 2 times f of 3 is less than 0, not less equal to, is less than 0 strictly, just be less than 0, is less than 0, then f of x, our function, ex minus 2x plus 5 equals to 0 has a real root, has a real root, between 2 and 3, something like that. Or you can simply say, then the function, then the function of this lies between 2 and 3, something like that. Remember, I will say this function may have many other roots, but we're looking at the one that lies between 2 and 3. Or you can say, since there is change in sign, since there is change in sign, then this function here, x exponent x minus 2x plus 5 equals to 0 has a root between x between 2 and 3, something like that. Yeah, so that's what you do with that. When you're using sign change approach, that's what you do simply. Let's look at another example and see what you do with it. Another example, sorry. Example next, we're saying show that there exists a real root for the function 2x squared plus 3x minus 3 between x equals negative 3 and x equals negative 2. They want us to show that the root is there. Let's see if the root is there or not by using sign change approach. Of course, we shall have solution. Solution, I highlight this. So, like we've just done with part A, you do the same here. You simply get f of get. You first of all define your function. Let f of x be equivalent to 2x squared plus 3x minus 3. That's what we have. So our f of negative 2, let's start with negative 3, the same as 2 into negative 3 squared plus 3 into negative 3 minus 3. What does this give us? Of course, this gives us 9, 18, 18 minus 9, that's 9. This gives us 6. That is our f of negative 3. What about f of negative 2? What will it give you? Of course, 2 into negative 2 squared plus 3 into negative 2 minus 3. What does it give you? This will be 4, 8. 8 minus 6 gives you 2, and this gives you negative 1 already. So at this point, you can get f of negative 3 times f of negative 2. This gives us 6 times negative 1, which gives us negative 6. So you simply say, since f of negative 3 times f of negative 2 is less than 0, not less equal to, I don't know, in my hand, so much wants that symbol. Is less than 0, then what the question is, show that the root exists. Show that there is a real root of the function. Then there is a real root. We just use that there is a real root. A real root. Let me create more space. Okay, let me just proceed this side. And there is a real root of the function 2x squared plus 3x minus 3 equals 0 between x equals negative 3 and x equals negative 2. This is very important. The conclusion is very important. You don't write your work and you don't conclude. If you don't conclude, of course, you lose out the marks. So you have to always conclude. They wanted you to show that the root is there. You found this negative, this positive. Then how do you conclude? You have to conclude like that. Or you say, or you can say, or since there is change in sign, there is change in sign, then 2x squared plus 3x minus 3 equals 0 has a real root between x equals to negative 3 and x equals negative 2. Yeah, that's what we do. Those are the two ways you are supposed to conclude. Now let's go to example 3. This is just now to make us, I'll share the concept. You now pick the concept. But at this point, we're simply trying to look at different ways the question can be said. This time around, I'm bringing in natural log. They're saying Solution. So here, saying show that x plus log x equals to 0.5 has a real root between x equals to 0.5 and x equals to 1. Show that x plus log e, that's the natural log of x, equals 0.5 has a real root between x equals 0.5 and x equals to 1. So in this case, we shall first of all rearrange our equation. In this case, you have to rearrange the equation. We shall have x plus log e of x, that is ln or natural log, minus 0.5 equals to 0. Remember, we said our equation should be in the form f of x equals to 0. So that means that we should have a 0 term on one side. So we say let, we shall now say let f of x be equivalent to x plus natural log of x minus 0.5, something like that. And at this point, you start getting what is your f of 0.5. F of 0.5 will be the same as 0.5 plus the natural log. This is log e of 0.5 minus 0.5. Of course, now this and this will cancel. Shall be left with only the log of 0.5, or natural log of 0.5, which will give us, let me check here on the calculator, natural log of 0.5. Natural log of 0.5, which is negative 0.6931. This is negative 0.6931. That's what we get from that. Then what about f of 1? F of 1 would be equivalent to 1 plus the natural log of 1 minus 0.5. And this now gives us, still on the calculator, let me check. This gives us, when you get that, this is, gives us positive 0.5. Of course, yeah, that we know, because log, natural log of 1 will give us 0. So this gives us 0.5, like that, 0.5. Now, at this point, we've already seen that, yes, the root exists because it's changing sign, but we need to conclude. We also have to conclude this. And how will you conclude? Of course, you start by getting f of 0.5 times f of 1, which will be the same as negative 0.6931 times 0.5, which will give us 0.3 something, 0.3466, negative 0.3466. So here we shall simply say, since f of 0.5 times f of 1 is less than 0, then our function, then x plus natural log of x equals to 0.5 has a real root. Did I say real root? Has a real root, yes, has a real root. Between x equals to 0.5 and x equals to 1. As simple as that. That's what we do with that question. We simply substitute and conclude. Substitute if it's not, if the equation is, if it's not in the form f of x equals to 0, you form it by rearranging it. So let's look at this one also. This one, they're saying, show that the real root of show that there is a real root for 2x squared equals to 6x plus 3 in the range. This That range is like now our interval. The range is that. So let's see here, solution. Solution. I have to highlight this. Solution. So still, we need to rearrange this since it's not in the form f of x equals to 0. So I'll say 2x squared minus 6x minus 3 is equals to 0. Then I let my f of x be the same as 2x squared minus 6x. Remember, we're going to get f of 4. We need to first define our function in terms of x. So we shall have this. Then we shall have what is f of 3. By substituting 3 here, I have 2 into 3 squared minus 6 into 3 minus 3. So this becomes, of course, this is 18 minus 9. This becomes 6, something like that. Then I also get f of 4. F of 4 will be the same as cos 2 into 4 squared minus 6 into 4 minus 3. This becomes f of 4 will be the same as this is 16, 32 minus 24 minus 24 minus 3. 32 minus 24, this will be 8. This will be 8 minus 3, this gives me 5. It gives me 5. Now, what is my f of 3 times f of 4? This will be the same as, of course, both of them have given me positive. This has given me, if you put 3, it becomes, this is 9. If you put 3, this is 9, 18. 18 minus 18, oh, this is not the correct value, it is 18 minus 18. So 18 minus 18, this becomes negative 3. Because this is 9, 18 minus 18, I am left with negative 3. So this will be negative 3 times 5, which gives me negative 15. Then we simply conclude by saying, since f of 3 times f of 4 is less than 0, then our equation 2x squared equals 6x plus 3 has a real root. So that has a real root, in the range, range 3, 4. That's what you do with that. So that marks the end of those. Remember the first question and the second one, we just learned. This one we're looking at why you should bring them to one side and define your function as f of x equals 0. Now the next one, we're going to look at another concept. When you have trig ratios, what do you do? When you have trig ratios, what do you do? You recall from graphical approach that whenever we had trig ratios, we have to operate our calculator in radians. We're supposed to change our calculator to radians. So let's have the solution. Let me highlight this. Solution. Now, here we still, first of all, let our f of x be the same as exponent of 2x sine x minus 1. I told you how to put this in a calculator the other time. So we go straight forward to f of 0.1. What's our f of 0.1? To be exponent of 2 times 0.1 sine of 0.1 minus 1. what do you get? Let me run the calculator. Your calculator has to be in radians. In this case, let me put a very big note here. Your calculator has to be in radians. Change the calculator to rad mode. Change your calculator to rad mode. This is what you should take note of, because the values you're dealing with are very small. They are very small values, so your calculator has to be in radian mode. Okay, so this is what you should take note of while dealing with this. So in rad mode, what will I get? Let me get the answer here. Rad mode, we shall get f of 0.1 as negative 0.8781. Negative 0.8781, that is f of 0.1. Then my f of 0.8 will be the same as, of course, exponent 2 into 0.8, sine of 0.8 minus 1. This gives me, that is f of 0.8. That gives me f of 0.8, 2.55831. 2.5531. Then I go ahead and get my f of 0.1 times f of 0.8. What will it give me? It will give me negative 2.2419. Negative 2.2419. Then you go ahead and conclude. Since f of 0.1 into f of, let me delete this. Since f of 0.1 times f of 0.8 is less than 0, then our function exponent 2x sine x minus 1 has a real root, in the interval, interval 0.1, 0.8, something like that. That's what we do in that case, since they have. But the most important thing in this question is operating your calculator in rad mode. I remember emphasizing that already in graphical approach. I don't need to again emphasize it again, but you should know. You should know that the calculator has to be operated in the rad mode. Then this one is also a trig function, and we need to operate our calculator in radian mode. Solution. We are seeing a turn somewhere, so our calculator has to be in rad mode, but then also make sure that our function is in the form f of x equals to 0. So we shall start with 2x minus tan x equals to 0. Then you let f of x to be equivalent to 2x minus tan x, something like that. Then you proceed. Calculator has to be in rad mode. Still, change the calculator to radian mode, for trig to rad mode, for trig ratios, trigonometry ratios. So make sure you operate your calculator in radians, otherwise you end up getting wrong values. because these are very small angles. These are not angles in degrees. No, if they say between 30 and 40, that it becomes very complicated. So always operate your calculator in red mode when you find trig ratios. So at this point, my f of what 1.1 will be the same as 2 times 1.1 minus tan of 1.1. What does this give me? Calculator, we shall have 1.1 gives me 0.2352. 0.2352, something like that. Then f of 1.2 will be the same as 2 into 1.2 minus tangent of 1.2, which will give me what? That will give me negative 0.0405. Negative 0.0405. Now then I go to f of 1.1 times f of 1.2. What will it give me? Of course, this will be the same as 0.2352 times negative 0.0405. This gives me finally to give me what? To give me the other one is 0.1722. This is 0.1722. I put a wrong value. 0.7122. This one here. 0.7122. I'm using green. This is 0.7122. Which one was negative? This negative was negative 0.7122. This one. So times negative 0.7122, I will end up with negative 0.0405, I think. Yeah. So that's what I'll end up with. Then you conclude again. Say since f of 1.1 times f of 1.2 is less than 0, then our function, then 2x equals to tan x has a real root between 1.1 and 1.2, like that. 1.1 and 1.2. Excuse me. So that's what we do. By the time you reach, just by when you reach this point here, this one here, you already know that the root exists, but you need to conclude. And of course, you have two ways of conclusion. Concluding. I show you the first part. And you can still use the second part to conclude. The second method I showed you, you can simply say since it's changing sign, the root exists, or you can simply use this other approach. Okay, so let's wind up with these three examples. The last three examples, they are unique. They are a bit different. You see that each pair of examples, 1 and 2 had their own concept, 3 and 4 had their own concept, 5 and 6 had trig ratios. Now 6 and 7, we're looking at an instance where the root, this function has two real roots. Where this function has two real roots in the two given intervals. So how do you handle such a question? Of course, it's not challenging. You simply do the same with the roots given. So here I'll say, I'll simply say let my f of x be equivalent to 2x squared plus 3x minus 3, something like that. So after letting it, you'll get Of course, let's start with 0, 1. What is f of 0? F of 0 will be 2 into 0 squared plus 3 into 0 minus 3, which gives me what? Negative 3. What is f of 1? F of 1 will be the same as 2 into 1 squared plus 3 into 1 minus 3. What will this give me? This will be 2 plus 3, that's 5. Of course, and that's using positive 2. So, what is f of 0 times f of 1? That gives me what? Negative 3 times 2, which gives me negative 6. Then we can continue and even deal with what is f of negative 3. This will be the same as 2 into negative 3 squared plus 3 into negative 3 minus 3, which gives me, this is 9, 18. 18 minus 9, that gives me 9, and this gives me 6. What is f of negative 2? This will be the same as 2 into negative 2 squared plus 3 into negative 2 minus 3. This gives me what? This is 4. 8. 8 minus 6. 8 minus 6 is 2. This is minus 1. So we say since, what is f of negative 3 times f of negative 2? This gives me 6 times negative 1, it is negative 6. And you simply say since f of 0 times f of 1 is less than 0, and f of negative 3 times f of negative 2 is also less than 0, then 2x squared plus 3x minus 3 equals to 0. That function has roots between in the intervals, not even between. Let's try to maintain the language given in the question. Has roots in intervals. Has roots in the intervals. Has roots in the intervals. In the intervals 0, 1 and negative 3, negative 2, like that. So it has roots in those intervals. The other one, the other last. So in that case, the function has, they would have given you by the, now in this case, of course, let me try to sketch for you this one here and try and make you visualize what we're talking about. You have a function. You have a function, and when you plot it, something like that, you have this is something like that. So when I put 0, let's say my 0 is here. My 0 is here. My 1 is here. My negative 2 is here. And let's say negative 3 is there. When I put negative 3, what did I get? When I put 0, what did I get? I got negative 3. So 0 gave me negative 5, maybe somewhere here. Maybe negative 3 somewhere, so it gave me that. When I put 1, it gave me, when I put 1, it gave me 2. When I put 1, it gave me 2, so maybe somewhere there. Notice that this graph is cutting the x-axis in this interval, it is cutting the x-axis like that. Then when I put negative 3, what did it give me? It gave me positive 6, somewhere this way. When I put negative 2, what did it give me? It gave me negative 1, somewhere here. So you notice that it's still crossing the x-axis in that interval. So it is crossing the x-axis twice, between negative 3 and negative 2 and 0, also between 0 and 1. Now, what if they gave you the interval? If they had said negative 3 and 1, the interval negative 3 and 1, of course, -3 would have given you the 6. Negative would have given you the +6, and 1 would have given you also +2, and you would think the function has no root in those intervals, in that interval. Yet it has 2 real roots. So in that case, they would have said sure it has roots in the interval. Maybe -3, +1. In that case, you end up, you split the domain, you split up the domain and investigate, which we're going to look at that in the near future. And of course, that's the very way you do number 8. You do it in the same way. I'm not going to do number 8 because it is carrying the same concept. It is the same concept. You simply get f of -3, get f of -2, get f of 0, get f of 1, get f of 2, get with their corresponding products, simply f of -3, f of -2, f of 0, f of 1. You're multiplying them, then you conclude like you've concluded here. So lastly, example 9 is also special in its way. In this case, they are giving us a wide domain, a continuous domain. This one is taking on exact values, -3 to it is discrete. This one is continuous. They're saying between -3 and what? -3 and +3. So here what we do, we split the domain and investigate. We split it and study the behavior of the function within the whole domain. So I'll simply say, let's say solution. We go to solution. So under this solution, we have, under this solution, we're going to split the domain. So we're going to have x values in the form of a table. So I'm going to draw some simple table here. We shall have a simple table. I don't know that I can generate a line, something like that. Then I'll have the x values and I'll have the f of x values. Of course, I need to first define my function. Something like this. Then I have that. So this is what I have. So I'm starting from -3, then I have -2, then I have 0, and then I have 1, I have 2, and I have lastly 3. In this case, I split because I don't know. They're saying sure that the 3 roots of the equation this lie in the interval. I mean, locate, they're simply saying locate the roots of the equation this. They want us to locate them. We don't know where they are. You may be there when the root is between -3 and -2, or it is between -2 and 0. So we have to split the domain and investigate so that we establish where exactly the root lies. So we shall say let f of x be the same as x cubed minus 3x plus 1. That's our first definition. We're defining the function we're going to use. That we don't just use f of x anyhow without knowing what it's standing for. So from there, we're simply going to substitute these values in the function. Substitute them and generate those values. We shall have, of course, using the earlier approach, you would have split, then afterwards you plot. But in this case, we're not going to plot. We're going to get the values, then study. Look at the relationship between the values, and then we establish where the root lies. So when I put -3 here, this will be -27 plus 27. So this will give me 1. When I put -2, this will be -8 plus 6. -8 plus 6. That gives me -2 plus 1, -1. I'll have that. When I put 0, it gives me 1. When I put 1, this will be 1 minus 3, -2 plus 1, -1. When I put 2, +2, this becomes +8 minus 6. This becomes 3. When I put 3, this is +27. +27 minus 27, this becomes 1. Hope these values are correct. Let me check. Let me try to double check. Now put negative, this -27. This becomes +27. It gives me 1. When I put -2, this becomes -8. Negative 8 plus 6 gives me negative 2 plus 1 gives me negative 1. When I put 0, it is positive 1. When I put 1, this is 1 minus 3, negative 2 plus 1, negative 1. When I put 3, this becomes 27. When I put 2, this becomes 8. 8 minus 6 is 2 plus 1 becomes 3. When I put 1 again, 1, this is 1 minus 3. This becomes, I'm putting not 1, I'm putting 3. 3, this becomes 27 minus 27. 27 minus 9. 27 minus 9, that becomes 18. 18 plus 1, 19. So this is 27 minus 9, 18. 18 plus 1, 19. Then here this is negative 27. Negative 27 minus 9, that's negative 37. Negative 27 minus 9, that becomes negative 36. Negative 36 plus 1, that becomes negative 35. What mathematics is here? Negative 35. Okay. So we have negative 27 minus 9, that becomes negative 36 plus 1 becomes negative 35. This is negative 2. When I put it, it becomes negative 8. Then plus 6. Negative, this is correct. This is correct. This is, we shall have, when I put 1, that becomes 1 minus 3, negative 2 plus 1, negative 1. 2, this is 8. 8 minus 6, 2, 3. When I put 3, this is 27 minus 9, 18 plus 1, 19. I think this is now fine. You double check. That's why it is always good to double check your values. Otherwise, you may use wrong values. Now, like here, this was very wrong. Okay, so I'm now going to check is there a root between negative 3 and negative 2? Or is there a root between negative 3 and negative 2? Is there a root between negative 2 and 0? Is there a root between 0 and 1? Is there a root between 1 and 2? Is there a root between 2 and 3? Like that. So I check by getting what is f of negative 3 times f of negative 2. This will be the same as negative 35 times negative 1, which gives me 35 positive. You see? Then I look for f of negative 2 times f of negative 1. What does it give me? F of negative 2 times, I forgot negative 1 in the table. Oh, this is terrible. So let me put negative 1 here. I forgot negative 1. When I put negative 1 around here, this will be negative 1 plus 3. Negative 1 plus 3 is 2. This gives me 3. Negative 1 plus 3 is 2. That gives me negative 1. Yeah. Plus 3 is 2. Plus 1 gives me 3. Like that. So what is f of negative 2 times f of negative 1? This becomes negative 1 times 3, and that gives me negative 3. What is f of negative, what is f of negative 1 times f of 0? F of negative 1 times f of 0, that would be the same as 3 times 1, and that gives me 3. What is f of 0 times f of 1? That would be 1 times negative 1. It gives me negative 1. What is f of 1 times f of 2? f of 1 times f of 2, that will be negative 1 times 3, which gives me negative 3. That's f of 1 times f of 2. F of 1 times, then f of 2 times f of 3. F of 2 times f of 3, this will be 3 times 19. That gives me what? This is 30 plus, that is 57. Something like that. So we finished all of them. So here we observe which ones have given me values less than 0 and which one have given me values above 0. I'll come and check. This has given me greater. This has given me, yes, there's one here, there's another one here, there's another one here. Now so we shall conclude by saying since f of negative 2 minus f of negative 1 is less than 0, comma, f of 0 times f of 1 is less than 0, and f of what? F of 1 times f of 2 is less than 0, then the function we have then x cubed minus 3x plus 1 equals to 0 has 3 roots or real roots in the intervals. You can set the intervals, or you can set the whole interval. In the intervals, since you're locating them, -2, -1, something like that. Then which other one? Which other interval? 0, 1, like that. Which other one? And what? And 1, 2. Yeah. So that's what you do with this sign change approach. All these examples, the 9 examples, bring out different concepts that I think if you're attentive while watching, you understand sign change method. I think this will be of great help. I also have a summary of the points, the key points. We are saying, given a function f of x and the domain, how do you start up the question? Simply substitute f of a and f. Substitute a in f of x and b in f of x to get f of values of f of a and values of f of b. Then you know this, not the signs of the values obtained above, that is f of a and f of b. The root exists only when there is change in sign. If the given domain has only one root, of course, sometimes the sign may not change, and in such cases, that means that the root means that the function has no root in that interval, or it may mean that maybe the function has more than one root. So this conclusion here, sign change, will apply if there is only one root in the domain. Then also you remember to operate your calculate and rad mode. This is very, very important. Some of you forget, people fail these numbers, always forget this. When you're dealing with big functions, big ratios, make sure your calculator is in radians. Then be careful with the conclusion, this conclusion here. Of course, we shall always say since there's change in sign, the root exists. Sometimes the sign may not change, but there are more than one root. So we're saying, be careful with the conclusion f of a times f of that. It holds only when there is one real root in the interval ab. In cases where there is more than one root between a and b, you have to split the domain, like we did with the last part. The last part we had to split the domain because they were telling us to locate roots. You can't just use f of 3 and f of 3 and f of negative 3 and f of 3 and you conclude there is a root. Now here you can't say there is a real root between negative 3 and there is more than one real root in that interval. So you need to split the domain in that case. That's what this number 3 bulletin is telling us it holds only when there is one real root in the interval AB. In cases where there is more than one root between A and B, you have to split the domain like we've done with the last example. Then we use this approach, the sign change approach, when the question is open. That means that the question has not restricted you to graphical approach. When the question says, show that this one has a real root in this interval, you don't need to waste time again going to the graphical approach. Use the sign change approach. That is if they have not restricted, if the question has no restriction. But if they say graphical, go to graphical. If they simply say, show that the root exists, it is always a better deal going in for sign change method than going for graphical approach. Then you should attach a conclusion at the end of every answer. We've looked at that. Of course, in all my examples, I've been concluding. And some of you, I think, after watching this at this level, may think it has become monotonous and boring, but it is necessary. You have to conclude every answer that you get. You don't conclude, you lose the marks. Of course, there are two ways you can conclude. One of them is by getting a product, and if the product is less than 0, is negative, of course, less than 0, then you say the root exists. Or you can simply, just by observing the sign changing, -3 to positive, or +3 to negative, just conclude that since it's changing sign, the root exists. So you'll try out this example after, this question exercise here. After watching this, you can try out this. And you try out that example, then you reach me if you want to give me a feedback. For feedback, you can use Gmail Math. This is my email for mathematics, gmailmath@gmail.com. You'll forward your responses to this .com, or yeah, that's the only option you can use for feedback. But you can get more of this information, get more information on my YouTube channel, and subscribe, please. YouTube channel, that is Gmail Math. Yes, Gmail Math. That's the YouTube channel. Then you can visit my website. Visit my website. That is the website is gmailmath.com. gmailmath.com. You'll get more information, for more related information. Otherwise, thanks for watching. In case there are a few issues, I've given you the platform you can use. You can use gmailmath@gmail.com to get back to me. Subscribe to my YouTube channel, comment where necessary. If there are some few errors, things that you think you should improve, please feel free to give us a thumb up or thumb down, depending on what your reaction is. Yeah, thanks for watching and attending this lesson. We shall stop there for now. I'll see you in the next lesson.